Calculus 2, section 6.4, I believe class 3 or 4 or something. We're going to talk about the shell method, which is another way to find volumes as we rotate 2D shapes around either X or Y axis. And this one is going to be different than the disk method because now our representative rectangle is going to be parallel to the axis of rotation. And we are going to see that in some cases, it's better to use disk. In some cases, it's better to use shell. In some cases, you can use either or. And then in some cases, one will be impossible to use, so you will be forced to use. So in some problems, it will be pretty much preference which one to use. And in other problems would be you are stuck with using A or B method because the other one is not possible. So now let's write down the shell method. First of all, the way the shell method works, and I would need the bottle. There's the Coke bottle right there. Perfect. So if we are looking at any bottle, so what I have here is the bottle that is horizontal, right? We are going to imagine through the bottom and the cap, there is this axis of symmetry around which we rotate. And what are we rotating? We're rotating this function on top for disk method or shell method, doesn't matter. So as you rotate whatever this function is, which you can actually describe using the piecewise functions, as you start rotating that function, it actually gets you the shape of the bottle. So it has to be radially symmetric, right? And the disk method was your axis of symmetry goes horizontal here, but your cuts will be vertical, cutting out little disks. And if the two functions are involved, those disks will actually be washers because they would have the hole inside. And we talked last time about the CD or Blu-ray disc, right? It has a hole, so that's a washer. The CD is a washer. And if that hole was not there, if it was the full of material around, there will be a disc. So think about this. I take favorite cutting thing like a sword, and you cut down, right? You would have a disc. And that's the reason why the first method is called the disk method. Now, shell method is going to have the same axis of rotation, symmetry, going through the object, through the cap. But the slicing now is not done perpendicular to the axis. It's done parallel to the axis. So as you can see, if I go through the bottle and I start cutting like this, I will be cutting shells off of it, right? There will be shells. Each piece that I cut off, it will look like a shell. Now, you know, for those of you who are actually interested in visualizing this stuff, guys, Play-Doh, it's not too late. All you need to do is you get the Play-Doh, roll it like this, right, and make something round. If you are more crafty than that, right, put some dents and stuff that are obviously symmetric. And then you take a piece of string, and you see when you cut perpendicular, you will always get discs. If you cut with the string along with the axis, you'll be getting shells. You can do this in your house for like $2 and actually see how these things work so that later on when you have to do your engineering, it is clear. And I said this a million times in class. No one will ever, ever, ever care if you can integrate. We have Mathematica. There's no issues there. As engineer, you have to figure things out with shapes. You have to be able to model the function, and you have to be able to set that integral up. And you also have to have ability to type that correctly in Mathematica. All right, so that's the set of skills that you need: a setup and type it in.
The link.
The Mathematica, yes, as soon as I get it.
Oh, you've
New
got
one.
it. Okay.
So I will be sending to everyone new Mathematica link. I think that the version 11 is up. The old one is 10.3 that I have. As soon as that is up, you will all get the link to install. Your licenses from last year should be up and expired. Mine is. If I start Mathematica, it just has the new. So I'm waiting as well. So shell method. I'm going to one more time go with a disk over here. Draw a cylinder, the cheapest possible shape that we could have. Show that the axis of rotation is right there, and then cut out a disk right there. That disk will have a very, very tiny delta x width. So it's a 3D disk. So that's the disk method. And now I'm going to draw exactly the same shape. Axis again of rotation is on x. But now cutting is done this way. And what I'm getting are shells. So this is called the shell method because you get shells as you cut. Observe that if you are doing a rotation on x, you get the delta y to be your thickness. So now, disk method, rotation around x, you have dx. Shell method, rotation around x, you have dy. What is the formula that we are going to explore? Volume is equal to 2 pi integral a to b. Now, what your textbook says is f of x, x times f of x dx, and that is for rotation around y. And your textbook also says 2 pi c to d of y, f of y dy if rotation is around x. And this should be opposite, obviously, because if they were the same, why would we do it, right? So shell method has x integral for rotation around y and y integral for rotation around x, which should be clear when you look at the pictures above. Now, I always loved the way that Larson dealt with this in his textbook. His formula looks a little bit different. It's more powerful. These two that are coming out for our book are a little bit restrictive. So the Larson book will give us the formula as integral, well, 2 pi, integral a to b, and then he would say p of y, h of y, dy, where p stands for position and h stands for height, and it allows you to set up much wider range of problems than what our formulas allow. Because in some cases, guys, your axis of rotation does not have to be actually x-axis or y-axis. They could be shifted. And if you don't want to mess with the shifting functions, then the method that is given in our textbook would not work at all. You would be forced to work with Larson method. So this p of x stands for position, and h of y stands for height. And the height is actually the function, and the position is either y or x. But then again, it could be 2 minus x or 5 minus y, depending if there is the axis of rotation is shifted to those values. So that's what we have for this. As you read the Larson book, which, as I said, is much easier to read, you will see the formula written this way, so you know exactly what's happening there. Which one you're going to use, that depends on you guys. It's completely up to you. Yes?
They're like the same formula. Why does that one work for more?
They're not the same formula because you see that you have h of y is your f of y. So h of y and f of y is the same thing.
Okay.
But the y and p of y are not the same thing. When you have a y, you are stuck with y. But when you have p of y, you could have 2 minus y, you have y plus 2, because the axis of rotation doesn't have to be at the x-axis. And that's the fundamental difference between the two methods.
So it's y at any position?
Any position, yeah.
Okay.
So now let's take a look at the cheapest possible problem done with both methods so that we can see how this actually works. So I'm just going to have y equals x, obviously, and we're going to rotate that around x-axis, and let's say put that on 0 to 2 on x-axis. So let's first do disk, and then we'll figure out the rest. Disk, and then we'll do the shell. So disk method, what do I have? Again, the graph for this is just a 45-degree line up to 2, which means we'll have this, and we are getting the cone. We are rotating around x-axis. This arrow looks like a heart. There we go. No hearts allowed, it's Calc2. Just blood, sweat, and tears. That's all it is. So this is where 2 is, and we will draw representative rectangle for disk. Obviously, it has to be parallel, and we have integral 0 to 2 of our function x squared dx, which is x cubed over 3, computed from 0 to 2. We get 8 over 3 pi. Drop these pi's. There we go. So that's the disk method, done in like 6 seconds. Now, we want to do the same problem using shell. We must get the same answer because it's the same thing. So now, for shell method, I have to draw the same picture. Still rotating around x, which means we'll be dealing with dy. And the cuts are done this way now. So we're getting little shells. So what's the volume? Well, the volume is 2 pi integral. And now if you look carefully, it's 0 to 2, but on y-axis. It goes from the bottom up. And now I have y times the function in terms of y, which is another y, times dy. Everyone okay with this? So the first y here is the y from the formula. And this y over here is x equals y, because we have to feed y function inside the dy integral, right? So x equals y. It used to be y equals x in the previous case. So x equals y, y equals x, the same thing. Split them. And
So that's the f of y. The x equals y is the f.
yes. And wait, this is double. I'm not happy now. I'm getting y squared 0 to 2, but I have 2 pi in front, so this is going to be 16 pi over 3. That's not good. All right, so what's wrong? No, disk is single pi, the formula. Yeah, disk is single pi, shell is 2 pi. This has to work out to be exactly the same. Otherwise, mathematics falls apart, and then the rest of the world with it. Yeah, but this is x cubed over 3. Yeah.
And the f of y is y.
Yes, because when you flip this one, you will get x is y. From 0 to 2. And I get 16 pi over 3, which is not good. I need to get 8 pi over 3. So something is wrong, and I'm trying to see what. One of these has something wrong. So let's go back to disk. Disk is going to swipe from 0 to 2, our representative rectangle dx goes from left, which is 0, to right. We have to square the function. Our function was x, and we are squaring it. And that's technically your pi r squared right there. And we integrate, we get x cubed over 3, and we go from 0 to 2, and we get 2 cubed is 8 over 3 pi. That looks good. Now we're going to the one on the bottom. We have the function to be y equal x, and then
You should have had it rotating around the y.
oh yeah, no, this is so wrong. The way I set it up is just this is.
I was wondering that's why you
this
had it
is-
that way instead of up.
No. It's supposed.
stays
No,
that
the
way?
picture stays this way. It's just that I completely failed on noticing that the function is okay. So here we go. It's okay. All good. This is what stays. Can't go back in time to say to the stream, skip to this point in time, and I am not going to put annotation for it. So, all right, guys. So we will go from scratch. The formula is y times f of y. Cool? So y times, but look at f of y. It is in between this function and this function. So it is 2 minus y, right there. Right minus left, and then dy. So I will point one more time to the idea area between two curves. You either have right minus left. Now, what was my mistake 5 minutes ago? I just had y over here. So what was that computing? It was computing this. Because it was y and then minus 0. So it's just y. See? That's the difference between this region and that region. This region here is x equals 2 minus x equals y. And you get this one. Again, x minus 2, x equals 2 minus x equals y. So it gives you this region here. If I just put y, then it's this region. And it's not good. So that was my mistake. And that's why I got the wrong answer. Now you compute this thing, it's going to work out to be 8 pi over 3. So this must work out to be 8 pi over 3. Otherwise I quit. And it's on stream.
Well done, homework.
So 2 pi integral 0 to 2. We have 2y minus y squared dy. And now we integrate. So I get 2 pi open parenthesis y squared over 2 and then cancels with the 2 minus y cubed over 3 from 0 to 2. It's 2 pi. Plug in 2. We get 4 minus 8 thirds. 4 times 3 is 12 minus 4 thirds. So 2 pi times 4 thirds. And there is the 8 pi over 3 which we needed. Yes?
Sorry.
Bless you.
Get used to it, guys.
Yeah.
So does that mean for the general formula then, is it not, okay, 2 pi integral AB, would it be f minus g dx, or would it be f minus, because that's how they did in the book, and then they did, okay, f of x minus g of x.
Yes. So let me just draw to answer that question and to reinforce that idea. I will draw two pictures and set two integrals, and then we'll see. So the first one, they will both have y equals x. Okay. So the first one, it's going to look like this, and I'm going to cut it here. Rotate around. Actually, no. Just leave it there. I'm going to rotate. No, I need to cut it. Rotate around x. And if I rotate around x, but what I'm doing now is I'm cutting it off here, but I'm using this piece, so it's actually going to look like this. So this is going to be empty, and this is where the material is. So I'm using this part of the curve and the integral is 2 pi integral c to d of just y times y dy. Now, I'm going to draw the problem we just had, like this. Oops, that's a terrible line. I'm going to again cut it right here, and now it's going to be this. So this is material here, and it's rotation, and it's x-axis, and it's y-axis. And this one is 2 pi integral c to d of y times, I'll call this line over here, I don't know, line L. So L minus y dy. So you referred to this one as just being f of y, and you said that this is some kind of f of y minus g of y, which is perfect. And I will draw, let me just make these representative rectangles actually red so we can see them better. So both of these pictures involve the same coordinate system, the same function, but the cut is at a different spot. So over here, the meat of the shape is touching the y-axis, right? So the most of the shape is there. So guys, this is going to look like a cylinder. Think of it as a cylinder, and then it's going to have a conical cut inside. So if you were to put something like this on the desk, this will go down, right? The edge on top would be extremely sharp because it ends at a point. Because the material is here, and the material is on the bottom, and the material goes right there. So it creates a sharp point here, and then that sharpness is going to extend around, but the inside, from this side, is empty in here, because the delta y is right here. This is where delta y is. So if this is delta y, that means that's where the material is. This is the empty part. So this would be some kind of, actually Coke cans are like that. If you are to cut them and right at the edge on top would be extremely sharp. You won't be able to drink. So, or you would have to be stupid to drink. But that's the idea. So you have a conical inside. Now looking at this one is cone. This is the ice cream cone that is filled with material. You can't put anything inside because it's all solid. And observe what the delta y is. So it's between these two functions. So it's right minus left. You can see that this rectangle is always touching this function, x equals to 2 in our previous case. X equals to 2 minus x equals to y. So 2 minus y. That's why our function is 2 minus y in the problem. And the one where I did it wrong is a completely different shape. Right? Completely different shape. Are we all agreeing on that? Play-Doh. I'm serious. Like, too bad you're not an artist going into ceramics. You have that wheel. Just keep making these things.
How did you do it with clay?
And then just carve it somehow.
Carve it somewhere.
Yep.
I don't know.
Or just get into pottery and get the wheel and get all that stuff and start,
No thank you.
Oh, it's wonderful, messy. It's a lot of dust, dirty hands. It's awesome. You should try it sometimes. There are those art places where you can actually go and make stuff on the wheel. And they show, well, what do you like to make? Well, some stuff for my Calculus 2 class. They're very basic shapes, nothing to worry about. You won't be working on a plate that has a dragon on it. It's just going to be a cylinder. If you can make it out of wood, then I think better. It's round, right? Knock the tree off somewhere, or find the tree that's already knocked down, and just chainsaw, get the pieces. Yeah. like 3 months ago, 3 months ago, I found out the chainsaw works awesome for the wood countertops.
Chainsaw.
I have pictures to prove. It was an awesome day. Don't try it at home, unless you're changing countertops. In that case, yeah.
What were you trying to get out of doing?
I think if there is demolition involved, it's free of charge. Free of charge. I would not charge RVCC anything if I were to deconstruct some knowledge, because that's easy.
You want to come down and take out some trees at my house? I don't have time right now to pull out a chainsaw and do it.
I gotta.
Chainsaw?
Let me pause the stream. I was just kidding. Dynamite. You see Anna say FBI like here in like 15 seconds. Oh yeah, we were watching your stream for years, waiting. All right, let's see another one of these. Another example, let's take a look at 36, for instance. It has a function y equals ln x. I hope you're familiar with that. It goes through 1, that's ln x. And they say at cut at 2, so let's say that's 2. And they want to cut here, so this is our region. And the beautiful thing about this one is that the rotation is around y. So when you have a shell method and rotation around y, that means dx, exactly. Awesome. So is anyone sad yet that it didn't work out nicely? No?
I'm sorry.
Do you see it? Do you see the issue? So y equals 0, y equal ln x, y equals 2, x equals 0. Those are the parameters. So those 4 lines bound this picture, and you can find them all, right? Y equals 0 is the part on x-axis, y equals 2 is the line all the way on top, ln x obviously, and x equals 0 is the vertical y-axis. So those 4 are given to you, and when those 4 are given to you, you should be able to generate this type of a graph on your own. Clearly these 2 will intersect somewhere. This is our x-axis. All right, so we are forced to use shell method. We are forced to use rotation around y. So both of those, so if you are forced to use shell and you are forced to rotate around y-axis, then you are forced to use dx, which in our case over here is going to amount to a little bit more annoying calculation than usual. Because observe what's happening on the bottom of the representative rectangle. It's going to switch the function. As soon as it switches the function, that means a separate integral. So part of the volume will be computed when you do the dx going from 0 to 1. And that's the first piece, is just a cylinder piece. And then to that you have to add this one over here, which I'm going to color now a different color. And the reason why you have to do that, again, is because delta x, which you are forced to use, is going to jump from one function to another function. So there is no way to use the entire thing in one integral. It's going to be the first integral from 0 to 1, and then the second integral from 1 to whatever the hell this intersection is. So now I'm going to erase the green shading and reshade this into green. and purple, or pink, or whatever this color is. And again, I have two of these because the integral has to switch. So now I will draw another dx here. So for the green, the volume integral is 2 pi integral 0 to 1, and we have x, and we just have the top function is 2. So we have 2 and then dx. So that's the green integral. Now I need to know what this intersection is. So 2 is equal to ln x. E both sides. X equals to e squared. So for the, what is this color? Is it purple or pink?
That's puce.
Puce? All right. So for the puce color, whatever the hell that is 2 pi 1 to e squared. Because we are only computing the puce. Come on, let's call it pink. So we're computing, no, purple. It's better purple. Like, look at, why? Look, that.
That's fine. I was
What's
messing
the obsession with this? Can we just have blues and normal color? So, call this purple. So purple part clearly starts at 1 and ends at e squared. E squared is about 10, right? It's good to go? No, it's too much. All right, fine. So it goes to e squared. So 1 to e squared. We still have x, because that's in the formula, times the function. Now, can anyone tell me the function? What should I write for the function part? Two minus ln x, good. 2 minus ln x dx. Observe that your representative rectangle is not touching the axis of rotation. It's away from it. So it is stuck between two functions. The function on top is y equals to 2. The function on the bottom is ln x. So 2 minus ln x, because the rectangle is not touching the axis of rotation. The axis of rotation is at, well, it's not touching, sorry, it's not touching x-axis. That's what I meant. Where the other one, right, if x-axis, then y is equal to 0. So technically, guys, it's always subtraction of the 2. But when you have this situation, it's minus 0, so we don't write it. You see, this is top minus bottom, so 2 minus 0. And this is 2 minus ln x. Do we all see that? Two minus 0 and 2 minus ln x. But we don't worry about writing minus 0. So now we put the volume, so these are the green and purple volumes. So now I put the entire volume together. I have 2 pi, open the big bracket, volume is 0 to 1. So integral 0 to 1 of 2x dx plus the integral 1 to e squared of 2x minus x ln x dx. Now there's a little issue here that we can't really solve this one yet. We can just set it up and just leave it be. Because it's in the future, in chapter 7, this portion here You don't even know yet what is you don't even know the integral of ln x on its own. You know that the integral of 1 over x gives you the answer ln x, but you don't know the integral of ln x. We studied that one in 7.2. Now this is even past that point. So you first learn just the integral of ln x, and then you learn the integral of x ln x with the techniques and methods and so on. So this is the setup, and at this point, what do you do? Well, when you get mathematical, now you have Wolfram alpha. Fire it up and plug it in, and you will get a number on the other end. Again, I am primarily interested in your ability to set it up properly, which is you learn that the shell method has the axis of rotation and the representative rectangle parallel. So if you are forced to use shell, you go and you say, all right, shell plus rotation around y means dx. And then you realize that as you draw dx is going to swipe to the right, and on the bottom, right, the bottom part of dx is going to jump from one function to another function, which means you have to have another integral. And I hope you guys see that there is no way to put these two integrals together at all. Their limits are not the same. Their function inside is not the same. And I hope you also see that part where the top of the function, I can't display the, oh, actually I can. It's going to be a little bit smaller, but yeah, try to see it. So I hope you guys see that the top function that the dx is swiping is always 2x, and it appears in both integrals, 2x. That's the top. And the bottom changes from -0 to minus x ln x. Do we all see that? I hope we do, right? So there's no way for us to put these integrals together. Even if you decide to break this into two integrals and just have 2x, you have to have the same limits in order to put them together, and you don't. So you actually have to compute two separate integrals. But as I said, you don't have the tools for it right now, so don't worry about it. We set it up, and we can now go back to the picture and argue, can I use disk method or washer, whatever, right, to actually solve this problem and see if I can actually do it at all? So I'm going to do it on the board first, and if it works out, I'm going to add it to the stream. I'm going to write it on because it might not work out. I have to try it first. So we're going to do this together. So I'm looking for it to work out for the disk method now. So this is the shape. This is where the rotation is. And I need to use the dy. Now look, dy is at least promising, but if I can't massage functions, I can't do it. Dy looks promising because the bottom always, or the left part, always derives this function here, and the right one, right, is always on this function. So at least it's promising that it's one integral. That's cool. But the issue is, problems that can't be done with one of the methods are those where you cannot flip the function. Remember that not every function can be solved in the terms of another function or another variable. So this puppy here is y equal ln x. This is your x equals 0. This is your y equals 0, and this is your y equals to 2. Now, if you want to use the disk method, so for disk, if you are rotating around y, that immediately means dy. Awesome, look, my limits are already there, right? So volume for the disk is going to be pi, 0 to 2. I have the limits because the representative rectangle is going to start on the bottom and rise and stop at 2, so 0 to 2. It's a disk method, so it's single pi, not 2 pi, single pi. And then I have to have functions. Awesome. This is, look what this is. This is x equals 0, right? So it's going to be minus 0, so we don't have to write it. So we just have this one squared. But the problem is that this is y equals ln x. I need it as x equals in terms of y. So we have to flip this one. So if I flip it, what do I get? X equals to x equals to what is it? What is it? How about that? E to the y. Thank you. Yes, e to the y. Very good. So I plug the e to the y here, and then I square that, right? Because this method squared dy. So what is this eventually equal to? E to the 2y. Can we integrate that? Can we integrate that? Yeah. U sub, right? Or you memorize the formula, whatever. So we can do this with with disk method. So I'm just going to go over here, do this, put sad face. That's not that sad. That's sad. Say can't integrate yet. Make sure the word yet is there because we are going to be. And we're going to switch into the disk method. Disk method will say that the disk plus rotation around y implies dy, whose integral for the volume is going to be pi 0 to 2 e to the y squared dy, which is pi integral 0 to 2 of e to the 2y dy, which is pi times, what's integral 2y? E to the 2y? Excellent. 2y divided by 2, computed from 0 to 2. Do we get to compute with 0? Because e to the 0 is 1, right? All right. So, plug in 2, it's e to the 4 over 2. So pi times e to the 4 over 2 minus 1/2. And that's the exact number. You can go get decimals if you like pain.
I'm sorry, how do you get from
We integrated over here if you're asking about that part.
that's the integral. Integral.
Yes.
The 2y over 2.
Yes. You can use u sub or you memorize that e to the kx is e to the kx over k.
That's right, k is 1/2.
Why is it down below? Just that's how it is.
It's u sub, right? So u sub, you will have to have derivative of 2y. Derivative of 2y is just 2. And then you would put the 2 over here, and then you have to counter it with 1/2 outside, right?
Okay.
So that's the 2 gets used up for u sub, and 1/2 survives, which is at the end that one.
So what you're saying with the u sub, if you can't remember the formula's incorrect, you can use u sub.
You can
That
use
one
u
you
sub.
like.
Yep. So now this is an awesome example because we see that using disk method in this case was far easier than the previous shell method on the same example. So shell method gave us 2 integrals, and one of them is a little bit tougher to compute, where the disk method gave us something that we already can compute, and it gave us 1 integral. So for a problem like this, it can be done both ways, either shell or disk, but the disk was far easier. There will be other problems where the shell is going to be much easier. And as I said, there are going to be those problems when one of the methods cannot be used at all. So usually that ends up if you have, you know, this situation, right? We talked about it. So this method, right, would not be whatever would this give us, whether it's disk or shell, depending, if both have dx. You can't do this problem at all using dx. You can also have the analog on this side. dy, not possible. So dy, not possible. And dx, Not possible. And if you have that situation that something is not possible, you actually have to switch the method. Because remember, you are always constrained by functions that are given to you. You don't get to change those. And you're also constrained with the axis of rotation that is given to you, because if you switch the axis of rotation, I already told you, it's not giving you the same volume. So you're stuck with the method, right? If you can't integrate in one method and that's required, well, it can't be done in that case. You have to figure out something else. Maybe make it out of Play-Doh and then just do the water displacement. I don't know. Yes?
Now for the LMX one, the one that you have up there,
Yeah.
we had to split it.
Mm-hmm.
Could you do something like that for the one that you said is not possible?
You can't split it over here because it's not symmetric. If you go like this, right?
I meant like, were they on top or they inside?
Like this?
Yes.
But you're still touching the top and the bottom,
Oh, okay. I see.
right?
Yeah.
So, such is life. Yeah. Unless you cut it this way, which introduces 1, 2, 3, 4 integrals. What do you mean, no thanks?
No.
The math is vast. We can do things. Next example? I guess those zippers that are, like really, yeah. We're going to go the double speed next class to get, guys, 6.5, 6.6, 6.7. We got to catch up a little bit. We stayed too long reviewing, I guess. So we'll have to pick up the pace. Otherwise, we'll be, chapter 8 by the end of the course. So class preps for the next class. Let me stop the stream.